Log on, tune in, find out. Another good idea from Cambridge.
This morning session on designs for discrete responses. Our first speaker is Divya Majumdar from the University of Illinois at Chicago, and he's going to be talking about optimal designs for 2 to the k experiments with binary responses.
Thanks, Dave. I'd like to thank the organizers for inviting me, and of course a big thanks for my co-authors for doing all the work and letting me travel. So what we are looking at is the problem of optimal designs for 2 to the k experiments with binary response. Now what we are focusing on is k factors, but these k factors have the levels of these factors, or the points, are fixed. So for instance, imagine qualitative factors like gender. So 2 to the k with qualitative factors, imagine qualitative factors, or even quantitative, where your levels are predetermined, and the response is binary, good or bad, yes or no. So outline of the talk, let's launch straight ahead with an example. So this is an example. So my co-authors thought that I should have several examples to convince you that this is a problem worth looking at. Gone are the days when we used to just work on problems because we wanted to work on those problems. So, but now it has to have some relevance. So it does have some relevance, and we found in the literature many problems of this nature. So this is a paper from 1997, Technometrics. And it was an experiment performed at the IIT Thompson laboratory that was originally reported by Martin Parker and Zenek. It's about windshield molding experiment. So this was a 2 to the 4 minus 1 experiment with 8,000 experimental units, and there were 4 factors at 2 levels: the polyfilm thickness, oil mixture ratio, material of gloves, and the condition of metal blanks. Now these were all taken at 2 levels. Certainly one of them, this one, you can argue cannot have more than 2 levels. So if you look at this, this is, so 2 to the 4 minus 1 is 8, 8 experimental units. And these are the y's. The y's are whether the molding was good or not. I mean, success is whether the molding was good or not. So the question that we ask is, can we do better than if we were to run, if we had 8 runs, should we do it like this? This is a regular fraction. So should we do a regular fraction, or are there other possibilities? If it's a regular fraction, there is no problem. I mean, we know a lot about these, but the regular fraction, their optimality, and they have enormously good properties, but those were all derived for the linear model, or most of the properties. What about this particular setup? What is the story here? So the common practice is to use uniform designs. That means however many. When we say common practice, we are really thinking about the linear model setup, honestly. And so over there, you take the same number of observations generally at every point, and we are thinking, we are wondering if that's a good one or not. And as I said, a fractional factorial design is often the way to go, because for a full factorial, the number of observations become very large. Not just that, the number of experimental conditions become very large, and as you shift from one experimental condition to another, in many situations or in many cases, there is a price to pay. So it's desirable to have fewer experimental conditions, not just fewer observations, fewer number of observations. So there are situations where we find the regular fractions to be good. situations where you should do something else. Here is another example where the response is whether or not a particular symptom is developed in mice. The factors are over there. Age is at 2 levels. A genetic factor, there is a dietary fat intake at 2 levels, chow diet or Western diet. If I were a mouse, I know which one I would prefer, but a gender is male or female, so that's the other one. Here is the experiment. These are the number of replicates. For some reason, I have not been able to figure out why exactly they took these numbers, but these are the numbers. Another example here, this was a very interesting paper. It was one of the premier papers in the area on smoking, a study of smoking. And so the outcome was binary, and it was an answer to the question, did you smoke tobacco cigarette in the past 7 days, and 6 factors, all of which, by the way, were genuine qualitative factors in this study. So we will start with a simple 2-square case, then we go to 2 to the k. Please stop me if I don't make sense. I'm sure I won't at many points. So we look at a 2 to the k experiment with qualitative factors, as we have seen, as I said. Suppose there are ni units. We are going to convert. We are going to assume that the total number of observations is fixed, and we are going to convert it to proportions and try to determine the optimal proportion. So let's start with d-optimality. By the way, I'm sure I won't get to it, but we have looked at some other optimality criteria. For example, a-optimality, which is probably very relevant in this case. It's harder to handle, as in most cases, and but we have some results which I'm not going to talk about today, but we do have some results, and we are working on that as well. So we look at suppose eta is the linear predictor, then we take the standard generalized linear model setup, and the information matrix is x prime wx, and so the d-optimality criteria maximizes this quantity, where p is the number of parameters, or you can just look at the determinant. And here W is the matrix, and these WIs will keep coming back in my talk. The way to think about WIs, I don't have to tell you, is that this is like the information available at that point. 1 over WI, which we will call VIs, is like a variance. So this is the setup. This is how we will be looking. We have looked at, I should say, mainly these link functions, although many of our results are in terms of WIs and VIs, so the specific link does not matter for that result. But the link functions are like this. W's are like this for the link for logit, probit, log-log, and complementary log-log. What's interesting is that if you plot W versus the success probability pi, then if you look at the solid line here, and I think this is worth noting here, this solid line is for the logit link. Now, first of all, it's symmetric. Secondly, it goes up to about 0.25, so it does not vary a whole lot. Now, if you let me go back here, if the W's were all equal, then it's not hard to see that this essentially reduces to a linear model. So, and the results should be similar. The regular fractions should be good, uniform designs should be good, and there is a wealth of literature for factorial designs, 2 to the k designs. So when you look at this and you see this, you start to wonder, maybe in comparison to the other link functions, the results for the logit link should be closer to the standard results or the linear model results, and that's what we get essentially. So here is the same picture, but as a function of eta, the different curves look similar. What's also a little interesting is that in this one too, this is the probit. This is also symmetric, but the log-log and the complementary log-log is not symmetric, and so that poses some interesting, that the results are different for those links. Some of the results, I should say. So for a two-square experiment, then here is what the criteria looks like. For a two-square experiment, there are only 4 levels. There are only 4 treatment combinations, and the X matrix would look like that. The first column would correspond to an intercept. We are looking at a main effects plan, so the first one is the main effect of one factor. Second column is the main effect of the other factor. The W matrix looks like this. The little w's are the informations. The p's are the proportion of observations at that point. And then if you write down this determinant, it looks like this. So this is a constant sitting outside. The w's are functions of the parameters beta, and LP is this, where the v's are the inverses of w's, and you have product of 3 of the p's, sum of products of three of the p's. Now this looks so simple. We spent a lot of time trying to find an analytic solution. We could not, and we thought it was us. It was not the problem. The problem was simple. We were not clever enough to do it, and so, but finally we came to the conclusion that we cannot do it, and I don't think there is a analytic solution even for this case. But we were able to, you see once again here, if you look at this expression, if all the w's are equal, the v's are equal, so it's just a matter of sum of the product of 3 p's, and that the solution or the set of p's that maximize that is p equals 1/4. So the uniform design maximizes in case w's are all equal, and as you might expect, in case w's are almost equal, that should be the answer too. And all right, so we do have some analytic results. For example, there are 3 parameters: the intercept, the main effect of the first factor, the main effect of the second factor. So you need at least 3 points, at least 3 experimental conditions. And so it turns out we were able to characterize a necessary and sufficient condition for the design to be supported on 3 points, and this is what it is. I have 10 minutes left. I have 39 slides. So we are doing well, I think, time-wise. All right, so this is the saturation condition in terms of the betas. You can see that we are so proud of our results, we cannot have a fewer slides. We have to show you everything. So this is, again, I think I should start going through these quicker, but roughly this shows the region where the saturation condition holds. In other words, when the saturation condition holds, the design is supported only on the minimal number, that's 3 points. So we call that a saturated design. Everything, let's say, suppose beta 0, the intercept is 1 plus or minus 1. Then whenever beta 1, beta 2 in absolute value is above this line, the saturated design should be good. And what we found was when we are in this region, we found several things. We found conditions for different designs to be optimal. We also looked at the robustness of the designs. When I say designs, by the way, I think I have not made this clear. So the W's are functions of the betas. Betas are unknown. So we take initial values. This is Chernov's local optimality. So we are looking for locally optimal designs. All right. So we consider, so now let's go to the more general case. Now, in the more general case, it's easy to see that the design exists, but the uniqueness is not always guaranteed. It's not very important to think about uniqueness. As long as we can identify one good design, I think should be pleased with that. So let's now suppose that the parameter of interest is beta 0, the intercept, and a bunch of betas. We have kept it beta 1, beta 2, beta d. This would include all the main effects and maybe some interactions. So here is a theorem which really helped us to develop everything. So this is an expression of the determinant or the criteria in terms of, so as a sum here. This is a determinant of a submatrix from the X with rows I1, I2, I d plus 1, and these are the corresponding product of W's and then the corresponding product of the P's, and then summed over all possible. Let me just show you what happens for the 2 cubed experiment. So for the 2 cubed experiment, d plus 1 is 4. There are d is 3 main effects, 1 intercept. So d plus 1 is 4. So there are 4 columns. There are 8 rows. So over in this expression, you would take a 4 by 4 submatrix of X. In other words, you would take any 4 rows. You would take 4 rows, take the submatrix of that, square it, and then multiply with this other corresponding other stuff, W's and P's. So there are 8 choose 4 or 70 terms in this expansion. And so from the previous theorem, one can prove now several other things, several results, and I'm going to actually skip a lot of the next few slides. One can show that for the optimal design, the optimal proportions are never larger than 1 over d plus 1. If it hits 1 over d plus 1, well, let me not go there right now. So, and then there are different things that we can do. We defined this particular function f(i)x, which helped us to develop algorithms. Now, in the interest of time, let me go past this. I do have, by the way, the paper is ready and it's available in a website. I'll give you the link. I'm really talking about 2 papers, one which has already appeared or will appear in Sinica that deals with the 2-square case, and the more general case is a paper that we have just about finished writing. I'm looking at the almost final version right now. I'm carrying that with me. All right. So this is a generalization of the saturation condition, but I should talk about EW designs. So what's an EW design? Suppose that so we need to know in order to use in order to obtain locally d-optimal designs, we need to know the betas. Now, if you do, normally you will not know the betas. So, if you don't know the betas, but you have some idea of their marginal distributions, then for the local points, if we take the average or the expectations of each of these beta i's as the initial value, that's what we call the expectation W, not the average of the betas, but you take the beta distribution and derive the average of the W's. If you take that, then you get use that as your beta, then you obtain what's called the EWD optimal design. It turns out that these designs are amazingly good in our simulations, in our analytic results. These come out as one of the very good alternatives. And what's pretty interesting is that they are very, very good surrogates for Bayes optimal designs. And I'll show you that. Let me show. Okay, this is an interesting slide. So, for any given link function, the regression coefficients are if the regression coefficients are independent with finite expectations, and they all have symmetric distribution about 0, then the uniform design is then the EWD optimal design is the uniform design. But that is nice. But look at this one. So suppose we were to 5 minutes. Thank you. Suppose we want a Bayes d-optimal design, which means that you take the d-optimality criteria, take the log, that's the standard thing to do, log of the determinant for various reasons, and then take the integral of that, or the expectation of that. You can show by Jensen's inequality that this is less than or equal to this. So this is exactly the criteria for our EW design, because the expectation can be brought in and here. Remember, W is a diagonal matrix with the WI's, which are the information at each point, multiplied by the PI's. So you simply, this just means that you take the expectations along the diagonals. So it turns out, for example, I'll give a couple of examples. The first example, it turns out that suppose you take let me go to the second example. Let's take a 2-cube main effects plan. Then here, let us suppose that, see, what happens is that there are four factors, there are 4 parameters, the constant and the 3 main effects. Let us imagine that the constant is uniform in this, and each of these betas is uniform in 0, 3. Now, why 0, 3? If you think about it, in most experiments, you should be able to figure out the sign of each betas, because the betas are linked with the x's. If x is, say, gender, you should be able to say, well, it increases or decreases as you go from male to female. And in that case, you should be able to pretty much say that the betas have to be positive or the betas have to be negative. So let's take, so this is, so let's take this prior. It turns out, in this case, the relative efficiency of the EW design with respect to the true Bayes design is not more than 99%. And not only that, it takes only 2.39 seconds to compute, whereas the Bayes design takes 121.73. And as we scale up to higher and higher levels of factorial, we have seen that this time difference becomes pretty huge. So there's a lot of savings for time, in terms of time. So there we have algorithms. We have 2 different algorithms which we have proven that they converge. We have studied fractional factorial designs. Now this is an express train that's running. I mean, no more stops. So the fractional factorial designs, we have some interesting conclusions. And the conclusions are that, let me just show you one picture. This is a 2-cubed design. We are looking at a 2-cubed, a half fraction. That means we are allowed, 2-cubed has 8 observations, 8 experimental conditions. We say we will run only 4, which it doesn't matter which 4, but we will run only 4. What is the best fraction? So what is the best half fraction? Here is a very simple case that I can that we can have nice pictures for. We have, of course, more complex cases that we have studied in the paper. But look at this. If beta 1 and beta 2 are 0, this x-axis corresponds to beta 0. The y-axis corresponds to beta 3. Then in this region, the regular fractions are optimal. In this region and this region, the regular fractions are not optimal. So it turns out if beta 1 and beta 2 are already 0, if the other ones are 0 or close to 0, regular fractions are optimal. So in some sense, regular fractions are optimal under the so-called null hypothesis situation. If you feel that some factors are strong, then regular fractions may not be the best place to take your observations. That I think is the message that we are getting right now. And I can talk a little bit more, and since I have 1 more minute, I should make good use of it. And here is a simulation that we ran, and this simulation gives you the percentage of times where for the 2-cubed, these are the 2 regular fractions. 1, 4, and 6, 7 is just the first, 4th, 6th, and 7th rows of the X matrix that I had shown you. That's 1 regular fraction. This is another regular fraction. If all the betas are uniform in this tiny interval around 0, and beta 0 is uniform here, then in 42% of the time, this regular fraction is optimal. In another 42%, the other one is optimal. But as you change and go to priors that don't include really 0, that are one side of 0 or the other, regular here, for example, regular fraction 1, 4, 6, 7 is only 0.07, is optimal in only 0.07% of the times. 1, 2, 3, 5 is optimal in 16% and so on. And the blue numbers over here are the percent of times when these designs are at least 95% efficient. So not only are they not optimal when we move away from prior symmetric around 0, but they are also not even 95% optimal. I just want to say go all the way since I have no time. Here are the conclusions. So we suggest, actually, let me just point out this one. We suggest the use of EW designs. These are easier to compute and highly efficient compared to Bayes. We have some interesting results about fractional factorials. The EW designs, by the way, turn out to be pretty robust. I couldn't talk about the robustness. We did study robustness quite extensively, robustness with respect to choice of the starting point. And here are the references. Well, thank you very much.
Is there a quick question or two for Dibian?
Yes. The trouble with this, of course, to some extent, as with Linda Haynes' talk yesterday, is trying to sort out all the special cases. And I would just like to make my standard comment to talks about design for generalized linear models. That is that if the means don't vary very much, the weights will be pretty much uniform, whatever the link. And then, as Cox showed in a paper, or argued in a paper in Biometrica, and I think 1988, that designs for the homoscedastic linear model then apply. Okay, so you got some of these results.
So we got exactly the same things, but it also seems to me what is interesting in what we found out, interesting to us at least, is that if you believe that some particular factor is strong, then the link,
In that case, certainly.
in that case the W's would reflect that, or the weights would reflect that. And if you do believe that, then you can do better than using the uniform design. And I think that more than anything else is the bottom line, but I entirely agree with you. And most of our results too are, it's probably shrouded by the clumsiness of my talk, but most of our results really are quite general, and we don't have to go case by case into the link functions too much. But thanks, that's good.
One more quick question.
Previous work on design for GLMs has looked more at averaging the betas themselves and using that to generate sort of middle ground design as opposed to averaging the W's. Hey, can you give just a quick sense of if you looked at that and whether that is competitive here, or averaging the W's gives you something much better?
We have looked at that. Averaging of W's gives much better result, and I have some of that here too. But
Okay, so let's thank Dibyan again.